Okay, so let me provide the overview for RAN Intelligent Controller course. So the RAN Intelligent Controller course covers the following. You have the RIC, the interfaces, the functional split, and the control loops, the architectures of the two RICs, as well as the applications. Then the functional split define how the functions of the control and distributed units are divided. Since we learned previously that we now have three main components for RAN, the remote radio unit, the distributed unit, and the centralized unit. All of them have a corresponding connection, like we have here the mid hall interface, the front hall interface, and the challenge is what will be the appropriate functions and protocols on each of the components. It depends on the use case and depends on what the mobile network operator needs. Okay, so I'll be discussing that in this lecture. Okay, so at the end of the course, the learner must be able to summarize RIC, then the functional split, explain the X apps and R apps, which are actually basically virtualized functions or applications running on the RAN intelligent controllers. You have and then differentiate the two RAN intelligent controller architectures. Okay, so before that, of course, we need to review briefly the ORAN architecture. This will act as a wrap up of course 402. And then later we'll discuss the RIC overview and functional split. Okay, this is the heart of this course. Okay, so let's first go to the review of ORAN architecture. We already learned that the radio access network is the one giving access to the user equipment through wireless communications through radio frequency. And this radio access network is connected to the core network via the transport network or the backhaul. Okay. So over time, there are different RAN generations from 2G, 3G, 4G, and 5G. Their names are different, but essentially the purpose of each one is the same. It is to provide access to the user equipment. Okay, so these are the names for each RAN generation. Okay, over time, originally we have traditional RAN, the non-split architecture wherein both RRU and BBU are co-located on the side, while the split architecture have a separation by using a front hall interface called CPRI. Then there are also other architectures like centralized RAN, wherein the BBUs are pulled in a centralized location. And then the front hall interface are actually a distribution of optical distribution network. Then there are also functions that are virtualized on the BBU and they are run on a commercial off-the-shelf servers on the cloud. This is when the virtualized RAN, this is the virtualized RAN architecture. Okay, so in all of these models or all of these architectures, everything is proprietary from the hardware until the interface and also the software. But for Open RAN, every physical component, the hardware, the server, the interface, they should be open or commercial off the shelf. The remote radio unit, BBU, are COTS-based hardware. BBU functions are virtualized on top of the COTS-based hardware. Front hall interface is also open. Okay, so the software may be proprietary, but essentially the hardware are all open to ensure that there will be interoperability among different devices, whether they are from a certain vendor or not from the same vendor. Okay, and then the RAN functions involve RU, DU, and CU, and the function specific functions protocols under each of this component is defined by the 3GPP functional split. Okay, so first of all, before going to that, now let's look at the general RAN protocols here. They are summarized here from the layer 1 of the OSI layer until layer 3. And each of them are assigned to certain RAN component, whether in RRU, BBU, and the CU and DU. Okay, so we're not going to into detail on this. Okay, so inside, or rather in the RAN architecture, we have this ORAN architecture, which was enhanced from the 3GPP design. The 3GPP design only includes the CU, DU, and RU. But for ORAN architecture, they also converted these three components into open. And then the front hall interface is also open. Here, the front hall interface is also open. You have the mid hall interface, the F1, and then the E2 interfaces, which is the interface from the near real-time RIC to all the components of the RAN, to CU, to DU, to RU, and also to other nodes. No, not necessarily just one node. It may access several nodes at the time. Okay, so what is the purpose of near real-time RIC? The purpose of RIC is, or this near real-time RIC, is to perform operations for optimization of the network resources, maybe to verify whether the traffic is, if where's the problem in the network operations or something like that. We'll be able to discuss this more in detail later. So when I say near real-time RIC, it's less than 1 second. All the tasks that are less than 1 second. And then we have the non-real-time RIC. It's on the SMO framework. It's connected to the near real-time RIC via the A1 interface. When you say non-real-time RIC, this would be different functions or different applications, tasks that require more than 1 second of latency. Perhaps you need to provide some sort of traffic forecasting in your whole network, or prepare a model to optimize the near real-time RIC. Anything that would require more than 1 second to process, it will be done by the non-real-time RIC. Okay? So, in addition to that, the SMO can connect to the components of the RAN using the O1 interface. As you can see here, O1, 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 and so on. The O2 interface is connected to the O cloud, and this is the one that may have further, maybe there's a need to access a storage device on the cloud or something like that. Okay, so this is the heart of the course 402, the deep dive into Open RAN architecture. This is where everything is discussed in general, or rather, everything is covered. Usually, this is what we need to really understand. Just take note as well of the legend here. For gray ones, these are 3GPP defined interface, and then the green ones are ORAN interfaces. You can go to this website, or just visit the documentations of ORAN, and then there's an architecture image as well. Okay. Okay, so another important architecture would be this ORAN Alliance Reference Architecture, which actually is just similar to the previous architecture. Main difference is just that in the next slide, you'll see that there are further details in the different parts. Like the SMO includes some design, inventory, policy, configuration. The near real-time RIC has details like radio connection management, mobility management, QoS management, interference management, and so on. Even a trained model coming from the non-real-time RAN intelligent controller. The CU can be multi-RAT, that means multiple radio access technology, but it's not limited to just the 5G, 4G. And then they are all virtualized, since we are assuming that everything is running on commercial off-the-shelf servers. Then of course, DU and RU. Okay. So let me now discuss further the RIC. So we have a RAN Intelligent Controller overview. We learned also in the previous course that the working groups for ORAN are as follows. Mostly for these courses, the important ones are working groups 1, 2, 3, and 1, 2, 3 until 5. Okay, so yung working group 2, that's non-real-time RIC and A1 interface. Remember, A1 is interface is the one connecting the non-real-time RIC and the near real-time RIC. And the purpose of this is for radio resource management, higher layer procedure optimization, policy optimization, and AI models. But for near real-time RIC and E2 interfaces, they are prepared by the working group 3. It is for control and optimization of the RAN elements and any fine-grained data collection over the E2 interfaces. Okay, so now let's proceed on the discussion of the RIC. Over time, there were already controllers in previous generations. So like in 2G, there is what we call a base station controller. And then in 3G, there is a radio network controller. And then in 4G, there's really no separate controller element. And there is an interface called X2 to connect to different E node Bs. And then for 5G, we have a G node B. Okay, so are just like the base stations. And then due to the combination of the network virtualization, eventually we were able to introduce the RIC. 5G applications often require low latency. So 5G specifications require the use of network function virtualization and software-defined networking, and for the purpose of optimization for control of the RAN. So this RIC enables a lot of functionalities like the network intelligence, resource control, resource assurance. And this is originally defined for 5G. The RIC is originally defined for 5G, but it can be modified or it can be updated to support not only 5G. It's the important thing is it can support the interoperability of different hardware and software components. It also leverages data analytics and AI platform for better resource management, such as for optimization like QoS, quality of service, slicing, network slicing, and mobility. So essentially, it is for optimization, and ultimately, this is to have an efficient RAN architecture or a radio access network. Okay, so there are two different frameworks two different RIC frameworks. One is the non-real-time RIC. The other one is the near real-time RIC. The non-real-time RIC is located on the SMO framework, and it communicates to other components via the A1 interface and O1 and O2 interface. Just go back to the Open RAN architecture, the ORAN architecture to verify the interface. This is used for tasks that require greater than 1 second of latency, like as mentioned earlier, more on configuration management, data analytics, maybe for forecasting. And this non-real-time RIC hosts what we call R apps. The R apps are possible proprietary applications to perform certain functions that would use the data collected by the near real-time RIC. Okay, so this can also include policy guidance, configuration management, and others. Okay, but what you need to know is anything greater than 1 second of latency that should be handled by the non-real-time RIC. Next, near real-time RIC framework is connected to other devices, other components. It's connected to the non-real-time RIC using the A1 interface, and then connects to others using the E2 interface. Now, if we go back to the architecture, there's an E2 interface here connecting the near real-time RIC to the CU, the DU of different nodes. Okay, so let me go back to the table earlier. Okay, so the near real-time RIC supports tasks that are less than 1 second of latency, like for example, radio resource management and other functionalities for the E node B and the G node B. Remember, this is like the base station for 4G and 5G. So we have here also X apps. This is the equivalent of our apps, but in near real-time rate. So non-real-time rate, R apps, near real-time rate, X apps. Okay, so this is the general Aura non-real-time rig architecture. So you can see non-real-time rig is on the SMO side. It's connected to the near real-time rig using A1 interface. And then later we'll discuss further on this. And then we have here the near real-time rig. This one contains the X apps. Its southbound interface is E2, northbound interface is A1, now towards the non-real-time breakdown. All of this are defined in the working group 3. Okay, so now let's proceed to the functional split. Remember what I said before? We know that the remote radio unit is separated from the baseband unit and are connected using the front hall interface. An example of this is the CPRI. But eventually, they realized there is a need to further split the functions of the BBU into CU and DU, so distributed unit and centralized unit. The separation is summarized by the technical report from 3GPP, the TR 38.801. Okay, so the split RAN architecture wherein BBU is split into DU and CU, and then there is now a new interface called the mid-hall interface. So now we have the front hall interface, the mid-hall interface, and the back-hall interface. Whatever the functions of the CU, DU, and RU or RGU, they are defined depending on the needs of the mobile network operator. Okay, so we will discuss this now in the next few slides. Okay, so what is functional split in 5G? Different protocols or different protocols reside in different components. Now, among the three, the RU, the DU, and CU. So split implementations make it more flexible and easier for mobile network operators to fit to specific deployment constraints. Now, maybe they just prefer to have the RU and DU at the same location, but the CU at a different location. Or maybe they can have the DU and CU at the same location, but the RU is separated. So depending on the needs of the mobile network operators, they can select which design that they want. Okay, so these are key factors in determining the split choice that the MNC would want: the specific quality of service, the user density, and the transport network. Okay, so these are the key factors for that. Okay, so here are the overview of the functional split. So for the monolithic RAN, we just have the BBU as is, same big block, and then we have the radio unit. But because of the technical report 38.801, the BBU became a CU and DU. The RAN functional split divides the monolithic RAN into three parts instead. You have the radio unit, distributed unit, and the centralized units. So we have a separation here by the mid-hall, and then we have the front hall here. So if the mobile network operator decides to have a split here at the bottom, between the RU and the CU and DU, then that is what they call a low layer split. It's at the bottom. It's a low layer split, LLS. If the mobile network operator just decides to split at the top, combining DU and RU in one main part, they'll just have a high layer split. So high layer split at this part. Okay. Combining the two, if you need to do separation for all three components, then you can use dual split, a combination of HLS and LLS. Okay, so let's first look at the high layer split options. So there are two options here, options 1 and options 2. For option 1, that is when we separate the following protocol. Okay, so the RRC and SDAP are on the centralized unit. So the functions here, the network functions, virtualized network functions, are on the CU COD server or CODS hardware, while all the others will be performed on the RU-DU system or RU-DU hardware. Okay. So here there are only two blocks, the CU and the integrated DU and RU. F1 is the interface between CU and DU. Okay, so this is the mid-hall interface. This is an open interface. This kind of deployment scenario, or rather these two deployment scenarios, options 1 and 2, are best for high capacity or capacity use cases in dense urban areas. And this one usually has a large dependence on the front haul performance than LLS. Okay. So the option 2 is just you consider PDCP protocol also in the CU. Okay, so next, if you consider low layer splits, what you do is you split the lower part of the RAN protocol stack, and then you'll get two blocks. One is the integrated CU and DU. The other one is the RU. Okay, so this is option 8. Only RF is assigned as a function of the remote radio unit. And then the PHY, MAC, RLC, and so on are assigned to the CU and DU. So in this kind of setup, LLS utilize less than perfect front-haul interface. Then this one is CU-DU, then RU. The lo-fi is performed at the RU, and then the hi-fi is considered at the option 6. Okay. So for option 6, there's a specific front haul interface. Usually it's the NFAPI. It's a functional application platform interface that is provided by SCF or Small Cell Forum. It is to allow SCU and SDU to connect to any SRU. Option 7 often use eCPRI frontal interface. And then option 8, later we'll see the option 8. There's a special option, sub-options for option 7. We have here the split option 7.3, split option 7.2, split option 7.2x, and 7.1. So they can further specify even on the particular protocol the certain processes. So maybe they want only this split here, or so on. Okay. So this is a more specific split for option 7. Then option 8 uses a CPRI interface. This was originally vendor specific, but can also use eCPRI for open interface. Okay, so to summarize, these are the different functional splits and where we split the RAN protocol stack. Option 1, 2, 3, 4, 5, 6, 7, 8. It's less common to use option 3, 4, and 5. So it's more common to use actually this high layer split and low layer splits. We can also see the interface since for options 1 and 2, we have the separation of the CU and the DU-RU. Therefore, we have a mid-haul interface. This is the F1. F1 is defined by 3GPP. And then for the low layer splits, the front haul interface connects the RU and the CU-DU. And depending on the option, we have different interfaces that is best used. For SCF, Small Cell Forum, we have NFAPI. For option 7, we have eCPRI. And option 8, eCPRI. So with all this flexibility, it makes it easier for operators and vendors to select a split variant according to their design and operational needs. Maybe they only need more RF devices, then they can just focus on option 8. Or maybe they only have existing infrastructure for option 6. Then they need a connection towards the RU with the functions low, phi, and RF. This is another way to view the functional split options. This is option 1, 2, 3, 4, 5, 6, 7, 8. It is like it's just rotated. You still have your CU, then DU, and RU. Okay. This pertain to the OSI layer, OSI layer 1, OSI layer 2, and OSI layer 3. Okay, so here are some sample deployment scenarios. If you have all of them separated, then that means there's an independent RU, DU, and CU locations. So the front hole, the mid hole exists. Usually the mid hole is kilometers, this also in kilometers. For another deployment scenario, we're in co-located or CU and DU are co-located. That means that there's actually no mid hole here. Then we only have front hole. What if we have co-located DU and RU? Then we don't have any front hole really, and we have mid hole here. Usually the front hole exists, but just tens of meters within the same building maybe, or this mid hole is connected like fiber optic cables. It's also possible to have all of them in one big block like this, RU, DU, and CU integration. Oftentimes, this is for small cell or hot spot scenarios. Hot spot scenarios. So small cell forums also define the functional split. They look at it as either an integrated solution or a disaggregated solution. When we say integrated solution, everything, all the three components, the RU, CU, DU are in one big product. But there are disaggregated solutions like this 2-product solution and 3-product solution. 2-product solutions are usually based on the options 2, 6, 7, and 8, where in each option there are only 2 blocks. Then in the 3-product solutions, it's usually the combination of the low layer split and the high layer split. Now, that's why there's a combination here. Option 2 and 6, option 2 and 7, and option 2 and 8. Okay, so other than the setup, now there are other reasons to choose different functional splits or different splits. No? It is depending on the delay, the performance, the bandwidth, but we'll not be able to go into detail on this. Okay, so let me go now to the R apps and X apps. So remember, R apps are the applications, the functions on the non-real-time architecture. X apps are in the near real-time architecture. So we can compare the two as shown on the table. So non-real-time RIC applications are tasks that require greater than 1 second of latency. And oftentimes the R apps are independent of the non-real-time RIC. So they are just on the same SMO. These are value-added microservices to support and facilitate RAN optimization operations, also policy guidance as mentioned earlier, enrichment information, configuration management, data analytics. So more on tasks that are not real time, so it may take longer time. Okay, so any application designed to run on near real time RIC, that would be in the X apps. Okay, so examples of our apps would be traffic forecasting, AI, and machine learning models. Okay, on the other hand, X apps are for applications, tasks that require less than 1 second of latency. And this is independent of the near real-time RIC, but it is on the near real-time RIC. But not the X apps may be different per mobile network operator, depending on what they want to accomplish. These microservices can be used to perform radio resource management through interfaces and service models. Maybe any model trained by our apps may be maybe relayed to the near real time RIC, and then the near real time RIC will operate that one. Some examples of EXA apps would be for scheduling, network slicing, and so on, for monitoring. Here are other examples for our apps. We can have our apps that are signal predictors. Maybe you need to find out where will be the location of UE. Why do we need to predict the location? So that we can prepare any handoff if necessary. Another one is this one, our AppU, cell utilization predictor, to predict the cell utilization over time and maybe understand whether there's a possibility of overloading that cell site or maybe underutilizing that cell site. Okay, the last one is the RFQ, measure the measurements of the UERF signal to predict later the capacity utilization and somehow look at the quality of experience of a user. So these are just some examples. Of course, there are so many more, not just this three. This is where the flexibility, freedom of the service providers will come into play. So even though the hardware and interfaces are open, the design of the software components may now be more competitive. Okay, XApp use cases on the other hand, this can be any automated network optimizations, use case specific RAN optimization, or any innovation in the RAN, like measurement, neighbor relation, admission control, no? Or maybe if it's not only just 5G, even the virtualized function of 2G, 3G, and so on. No? So Parallel Wireless prepared the virtualized network functions or XApps for the other radio access technology. So it's not just for the 5G. Okay, so XApps in general can be for live network data collection, testing the RAN, and so on. Okay, so in general, the main difference is that for non-real-time RIC, it's focused on our apps that require tasks for greater than 1 second of latency, while near real-time RIC is for X apps with with less than 1 second of latency. Okay, let me just go over briefly on this non-real-time RIC architecture. So this is the non-real-time RIC architecture. It has an A1 termination. The A1 interface is connected to the near real-time RIC. And then the O1 termination connects also to near real-time RIC and E2 nodes. You can also see O2 is connected to the cloud. The SMO is connected to the cloud and the other nodes. In the non-real-time RIC, there are a lot more information like this inherent functionality. Our apps are connected to the non-real-time RIC via R1. Our apps may be different across different vendors, different mobile network operators. There are even external sources here. If there's a need to communicate externally to another resource. Okay. Now let's proceed to the more specific architecture of the near real-time RIC architecture. This is the overview of the near real-time RIC internal architecture. Remember that the RICs are connected via the A1 interface, and the SMO also connects to the near real-time RIC via O1 interface. There are now near real-time RIC APIs here for XApps. Again, XApps are for radio resource management or any specific network slicing scheduling functions. Like conflict management, the subscription management services, security, radio network information base. E2, of course, is the interface from the near real-time RIC to the E2 nodes, specifically to the CU and BU. Okay, so here are some examples of the centralized near real-time RIC. So this is a near real-time RIC serving only 5G because as you can see, it's only the CU and the DU. And then also it can serve both 5G and 4G. You can see ORAN eNode B. eNode B is for 4G base stations. So it's possible also to serve both 4G and 5G, or even just serve 4G. So it's just connected to the eNode B. It is there's a prefix O because the assumption is that the interfaces, the hardware are all open and non-proprietary. Okay, so this is the centralized near real-time RIC. And then another way is distributed near real-time RIC, wherein there is a collection of near real-time RIC that can handle various components. Okay, so one physical near real-time RIC may consist of one or more logical near real-time RICs. No? They have one big block of physical hardware, but they are logically different. So they may connect to the non-real-time RIC at different A1 interfaces. Okay. So just to summarize, just to end this overview of the RIC architecture or of the RIC, we have learned that RIC enables the management of radio resources and radio networks. It enables eNode B, GNode B functionalities for network intelligence and resource assurance and resource control. eNode B is for 4G, GNode B is for 5G. The functional split defines how the RAN functions assigned to the components. And then these are the CUD and RU. And then the operators, vendors can decide which split variants they want to use depending on their design and operational needs. The three RAN control loops are non-RTRIC, near real-time, and the ODU, scheduler control loops. Our apps are microservices that facilitate RAN optimization and operations, including configuration management and data analytics. X apps are microservices that can be used to perform radio resource management, like, for example, network slicing, network scheduling, data collection, and things like that. Okay, so thank you very much for listening and joining today. I hope that you have learned a lot of things on my course overview. Okay.